Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last few lectures we studied FRF measurement using an impact hammer and a shaker. So once the FRFs have been measured, the next step is to find modal parameters from them. How this is done? This is done by curve fitting of the measured FRFs or IRFs. So in this and the next few lectures we are going to study modal parameter estimation methods, which are nothing but curve fitting methods. And in this particular lecture we are going to study modal parameter estimation using peak picking method, which is probably the simplest and most straightforward approach to modal parameter estimation. So what is modal parameter estimation? Modal parameter estimation refers to obtaining an estimate of the modal parameters from the measured FRFs. So we have the measured FRFs and then from that we have to obtain the modal parameters, that is the natural frequency, mode shapes and damping factors of different modes which are appearing in the FRF. So modal parameter estimation is also referred as curve fitting. This is because it essentially involves fitting a known theoretical relationship of the FRF and the model or IRF and the model to the measured FRF or IRF. That is why this process is also called curve fitting. So this also we discussed in a previous lecture when we talked about the principle of experimental model analysis. Modal parameter estimation is also sometimes referred as phase separation technique. This is because the FRF or IRF, it consists of contributions from different modes. So if we want to find modal parameters of different modes, then we need to separate the contributions of different modes to the FRF or the IRF, okay, and that is why it is also sometimes referred as phase separation technique to find the modal parameters. The modal parameter estimation methods or curve fitting methods are well advanced and established now, and there are several commercial software packages which are available which allow curve fitting using alternative approaches. However, we need to have a basic understanding of various approaches and the assumptions which are involved in them, okay, so that we can use the available tools correctly and effectively, and also we can take decisions about the acceptability and the validity of the results which are obtained by the software. Okay, and therefore our objective in this and the next few lectures in which we are going to talk about modal parameter estimation is to develop an understanding of the basic concepts of curve fitting and know the assumptions which are involved in various types of approaches. So let us now classify the curve fitting methods. So there are several ways curve fitting methods or modal parameter estimation methods can be classified. So one of the first type of classification is either single degree of freedom methods or multi degree of freedom methods. So single degree of freedom methods fit one mode at a time, okay, while multi degree of freedom method fit several modes in the FRF at a time. Then the classification can be based on whether the curve fitting is done in the frequency domain or time domain. So the frequency domain methods, they basically perform the curve fitting of the theoretical relationship of the FRF to the measured FRF, while the time domain methods, they perform the fitting of the relationship of the IRF to the measured IRF. Some time domain methods also enable using free responses to find the modal parameters. The other way the methods can be classified as either the local methods or the global methods. So the local methods of curve fitting, they perform fitting of one FRF at a time and then sequentially fitting every other measured FRF, while the global methods, they fit all the FRFs at a time, okay, in a single go they fit all the FRFs. Then there can be single reference methods or polyreference or multi-reference methods. So single reference methods process or feed the FRFs measured with respect to one reference position. So these methods feed either one row of the FRF or one column of the FRF that has been obtained by measurement. But the polyreference method or multi-reference method techniques feed the FRFs that have been obtained with respect to more than one reference position, right, and therefore the data of more than one row or more than one column is fitted using polyreference techniques. So let us now look at the method called peak picking method. This is probably the simplest and most straightforward approach to modal parameter estimation. So, it is a frequency domain method. So, it is going to feed the FRF expression to the measured FRF, and it is based on a single degree of freedom assumption. So, let us first of all look at what is this single degree of freedom assumption. Okay. So, this method, the peak picking method, assumes that the FRF in a narrow frequency band around the resonance peak is contributed by that mode alone. So, if we are, let us say, analyzing a particular peak in the FRF, right, let us say rth peak, and then this method assumes that the FRF in a narrow frequency band around that rth peak is contributed only by rth mode of the structure, right, and the other modes which also are present and also contribute to some extent the frequency response in that frequency range. However, that contribution is neglected by this method. Okay. So, therefore, the contribution of all the modes other than the mode being analyzed are neglected. So, let us try to see what is the implication on the FRF expression that we will have to fit when this assumption is made. Let us consider the case of structural damping. So, we are assuming that we are fitting a structural damping model to the measured FRFs. Okay. So, we know this relationship. Earlier we derived this relationship, which is alpha j k omega is equal to summation from r is equal to 1 to n. In the numerator we have phi j r into phi k r, which is the product of the jth and kth element of the rth mode, right, divided by omega r square minus omega square plus I eta r omega r square. So, here omega r is the natural frequency of the rth mode and eta r is the modal loss factor of the rth mode. Let us also define what is called as modal constant. So, the numerator, which is the product of phi j r and phi k r, we are defining as modal constant. So, this quantity here, so this numerator phi j r phi k r we are designating as r a j k, right, which is the modal constant of the rth mode with respect to the FRF alpha j k. So, with this change, now the numerator in the FRF expression is r a j k. So, let us say if we are focusing our attention on rth mode, then we can rewrite the FRF expression by separating the contribution of the rth mode and the contribution of all the remaining modes. So, you can see the first term here is here in this expression, this first term is the contribution of the rth mode, contribution, correct, and the second term is the contribution of all the other modes. This is contribution of all the other modes. Right. So, this method now assumes that the second term, which is the contribution of all the other modes, is negligible, right. So, when this is neglected, we end up with this approximate expression for the FRF, which only depends on the contribution of the rth mode which is being analyzed. Therefore, the conclusion is that now the FRF which we have measured, we are going to fit this expression, which is the simplified expression or the approximate expression, to the measured FRF. Okay. So, we are going to fit this expression to the narrow frequency band around the rth peak in the measured FRF. Now, how do you determine the natural frequency? So, the estimate of natural frequency omega r is taken as the frequency where the FRF magnitude is maximum. Therefore, wherever the FRF magnitude is maximum, natural frequency corresponds to that frequency. So, if you look at the FRF expression, what we see that omega is equal to omega r, the denominator is minimum, the magnitude of the denominator is minimum. So, this means that the FRF would be maximum at that frequency. So, this is the observation based on which the estimate of the natural frequency is made. Okay. Now, how modal loss factor is estimated in this method? This is estimated using the concept of half power bandwidth. What is half power bandwidth? Half power bandwidth is the width of the frequency band where the FRF magnitude drops by a factor of 1 by root 2. So, we should look at the maximum FRF magnitude and we should find the frequencies where the magnitude of the FRF drops by a factor of 1 by root 2 with respect to the maximum magnitude, and those points or those frequency points are referred as half power points. Why it is called half power? This terminology has come from the definition of electrical power. So, electrical power depends proportional to the square of the voltage. So, if the voltage changes from V to V by root 2, then the electrical power changes from V to P by 2, P to P by 2, right. So, the power becomes half when the voltage reduces by a factor of 1 by root 2. So, therefore, here also when the FRF magnitude drops by a factor of 1 by root 2, we say the power has dropped by half, and that is why the frequency points are referred as half power frequency points. So, let us work out an expression for half power frequency points or half power bandwidth. So, we are interested to know those frequencies at which the magnitude alpha j k, right, it becomes 1 by root 2 of the maximum FRF magnitude, which is the FRF magnitude at omega to omega r. So, this is the FRF magnitude at omega to omega r, and this happens to be the maximum FRF magnitude, right. So, this is maximum FRF magnitude, right, and this is nothing but the FRF magnitude at frequency omega, correct. So, when we use this equation, then we can now substitute on the left hand side the expression for the FRF based on the rth mode contribution, and on the right hand side we have the FRF magnitude at omega to omega r. So, if you solve this equation, then we get this expression that eta r omega r square is equal to plus minus omega r square minus omega square. So, this equation needs to be solved for omega in order to get the estimates of half power points. So, we have to solve this equation for omega. So, there would be two roots of this equation, and let us represent those roots by omega a and omega b. Those omega and omega b will be basically the half power points. So, we can write these expressions, and then if we assume that the natural frequency omega r is roughly the average of the half power points omega and a and omega b, and if you substitute this expression in the previous expression, then we get this result, that eta r is equal to omega b minus omega a upon omega r. So, here omega b minus omega a is the half power bandwidth. It is the width of the frequency range or the width of the frequency band where the FRF magnitude drops by a factor of 1 by root 2. So, therefore, if we can now determine half power points from the measured FRF, then using this expression we can determine the modal loss factor. How to now find modal constant? So, we have found now the natural frequency omega r, then we found the modal loss factor, and now the parameter which is left yet to be determined is modal constant, that is R A J K. Okay. So, this is the FRF expression based on single degree of freedom assumption, and so what we note at omega to omega r, right, at the natural frequency, we can obtain modal constant as R A J K is equal to I eta r omega r square into alpha j k at omega r. So, in this expression we note that eta r and omega r have already been found out, so they are known, and then the FRF amplitude alpha j k at omega r is also known from the measured FRF, and therefore, we can determine the modal constant of this rth mode for this particular FRF from this relationship. Let us now see that how we compute the mass normalized mode shapes, and let us now say that one row of the FRF matrix is available to us that has been measured, right. So, what we do? We determine now the modal constants for the rth mode of all the FRFs. So, for the driving point FRF alpha j j, we can write the modal constant expression as R A j j is equal to phi j r into phi j r, and therefore, the phi j r is equal to the square root of R A j j. So, if modal constant R A j j, which is the modal constant for the rth mode in the point FRF, this means that if we know R A j j, which is the modal constant of the rth mode or rth peak in the point FRF alpha j j, then we can determine the jth element of the rth mode shape from this expression. Okay. So, phi j r is nothing but the jth element of the rth mode shape. Now, once this has been determined, okay, now we can determine the remaining elements of the rth mode shape. So, let us look at the FRF alpha j k, which is a transfer FRF now. Okay. So, the relationship for the modal constant is R A j k, which is the modal constant of the rth mode in the FRF alpha jk. So, R A j k is equal to phi j r into phi k r, okay. And in this expression now phi j r has been already determined. So, therefore, the phi k r can be written as R A j k divided by phi j r, right. So, now we can determine phi k r, and now this can be done for various values of k from 1 to n. So, that uses all the elements of the rth mode shape, correct. So, we do it for k is equal to 1 to n, and then that uses the rth mode shape phi r, which consists of phi 1 r, phi 2 r, phi 2 phi n r. So, it is a column vector. So, in this way we get a mode shape, and we should note that this is the mass normalized mode shape, okay, because this corresponds to a unit modal mass. So, this estimate of mode shape corresponds to a unit modal mass, and that is why it is a mass normalized mode shape. Let us now take an example. So, we are going to simulate a modal parameter estimation using the peak picking method. So, we are going to now take a cantilever structure which we have utilized earlier also in the simulation of FRF measurement, right. And let us say there are 5 test points and we have measured a row of the FRF matrix. And let us focus our attention on analyzing the third peak in the point FRF alpha phi phi. So, this is the FRF alpha phi phi. So, we can see it is a point FRF, that is why we see between every two successive resonances there is an anti-resonance frequency. And now we first determine the natural frequency. So, we look at the peak magnitude for the third peak and we determine the frequency corresponding to that peak magnitude. That frequency is nothing but the natural frequency. So, we see from here that this frequency here, this frequency is nothing but 173.0 hertz, right. So, this frequency is 173.0 hertz, which corresponds to the maximum magnitude of the third peak, and in the radian per second this frequency of course would be 2 pi into 173 radians per second. So, in this way we get the estimate of the natural frequency. I think we should note that for a single degree of freedom with structural damping, the peak frequency matches with the natural frequency. But if the damping is of viscous type, that is if we have a single degree of freedom system with viscous damping, okay, then the peak frequency does not match with the natural frequency, it is lower than that. Of course, if the damping is small, then the difference is small, right, and the two can be considered to be very close or almost equal, right. However, the peak frequency theoretically is less than the natural frequency for a single degree of freedom system with viscous damping. For multi degree of freedom system, irrespective of the nature of damping, whether it is a structural damping or viscous damping, the peak frequency, the frequency of a peak in the FRF, and that does not match with the natural frequency of that particular corresponding mode, right. So, here of course, it is we are looking at a multi degree of freedom system, the cantilever structure, but of course, the peak picking method is based on a single degree of freedom assumption, and that is why we are assuming that in this method that the peak frequency is equal to the natural frequency, and therefore, natural frequency estimate is based on this consideration. Let us now determine the modal loss factor, and for that we determine the half power points. So, what we do, we focus our attention on a narrow frequency band around the third peak, right, and then we determine the frequencies corresponding to the FRF magnitude dropping by 3 dB. So, we can see this is the peak magnitude here, right, and then this is the reduction of dB by 3 decibels, correct. So, this is a drop by 3 dB. So, wherever this horizontal line at 3 dB drop intersects the FRF, at those points, at those intersection points, we get the half power points. So, this is first half power point, this is second half power point. So, therefore, this point is this half power point is 171.5, right, and this half power point is 174.25, correct. So, basically frequency range that was used for simulation was 0.25 hertz. So, we have frequency spacing of 0.25 hertz. So, once these half power points are obtained, now we use the expression eta 3 is equal to omega b minus omega upon omega 3, and then because the natural frequency already we have found out omega 3 is 173, basically we get an estimate of the modal loss factor, and which has turned out to be 0.015896, that is the modal loss factor. Now we analyze third peak in other FRFs and then find the estimate of natural frequency and loss factor for the third mode from the other FRFs, and in general these estimates would have some variance, right. There would be some difference in these estimates, and therefore to obtain a consistent estimate, a single consistent estimate, we take an average of all these estimates. So, we find average of the natural frequency estimates from different FRFs and modal loss factor estimates from different FRFs, and that gives us a single estimate of the natural frequency and modal loss factor. And if we do that, we end up with these results, that the natural frequency is 173 hertz or 2 pi into 173 radians per second, and the modal loss factor is 0.015914. Once these average estimates have been obtained, now we determine the modal constant for the third peak, and let us first of all determine the modal constant for the point FRF alpha 55, and the FRF magnitude f alpha 55 at the natural frequency is this, which can be obtained from the measured FRF, right. At the natural frequency we have determined at that frequency what is the FRF amplitude, that can be determined from the measured FRF, and then we use the expression for the modal constant. So, 3A55, which is the modal constant of the third peak or third mode in the FRF alpha 55, it is equal to I eta 3 average and then omega 3 average estimate square into alpha 55 at average estimate of the natural frequency. So, when all these values are substituted, which already are known, then we get an estimate of the modal constant. Then what we do? Extend this procedure of finding the modal constant to the third peak in other FRFs. So, in this case we need to now repeat this procedure for the remaining 4 FRFs. Once that has been done, then we can determine the mass normalized mode shape as we discussed previously, right. From all these modal constants we can find the mass normalized mode shape, and that mode shape turns out to be this. So, you can see it is a column vector with 5 elements, right, because there are 5 FRFs we measured corresponding to the translational DOFs at 5 test points on the cantilever structure. So, we get third mode shape consisting of 5 elements in it. So, in this way today we started our discussion of modal parameter estimation methods, and in this lecture today first we classified modal parameter estimation methods and then looked in detail the peak picking method of the modal parameter estimation. Now we stop here. Thank you.